I'm a rising junior at Brown University studying computer science and philosophy. This summer, my research was in computer vision with Professor David Chapman here at the University of Maryland, Baltimore County. We worked on edge detection using radon transforms and dynamic programming for indoor robotic navigation. Now, before we go into the research itself, I first want to discuss what computer vision is and why it's significant. So humans are very good at object detection. We're good at distinguishing a chair from a table from a desk. We know where edges are because we know where the physical boundaries of objects are. However, a computer, whether through a camera or an image on that computer, it can't inherently see objects. It only sees a grid of multicolored pixels. So in computer vision, we write algorithms and programs in order to help computers see the things we want them to see, such as objects, faces, or lines. So the goal of our research was to implement what's called the Approximate Discrete Radon Transform Algorithm, or ADRT, for line detection for the context of indoor robotic navigation. What this means is that we wanted to implement a software that could approximate a radon transform to find lines and edges in an image, so that a robot navigating around an indoor space could see the things in front of them so it doesn't bump into them. We also wanted to verify that this algorithm alleviates a problem known as fragmentation that tends to plague other line detection software. Fragmentation is where a line may be faint or broken and may not be completely obvious to a computer as one contiguous edge. This research is significant because radon transforms have rarely been used for line detection in the past due to the slow processing times of traditional implementations. So what is a radon transform? Well, in simplified terms, a radon transform uses polar coordinates, rho and theta, to find the density of an object or image at all points, rho theta around that image, in order to find things such as lines, curves, and gradients. But as I said before, while this will find us lines, it's not fast enough for our needs. We don't even need a full radon transform. We can make do with simply an approximation. One such approximation is called the hue transform. The hue transform uses those same polar coordinates, rho and theta. It looks at every rho and theta on the image, and at every rho and theta, it projects out a perpendicular line. It finds the brightness of every pixel on that line, sums them up, and then stores them in memory. This way, we have a brightness value associated with every single line in our image, so that the line with the highest brightness value is our most prominent edge. And while this is a perfectly good line detection software and a perfectly good approximation of a radon transform, it is still not fast enough for our needs, in which our results need to come in within a few seconds or less. So this is where ADRT comes in. ADRT depends on something called dynamic programming for its efficiency. Dynamic programming is an algorithm technique where a very large problem is broken down into smaller subproblems, which are then solved individually and stored in memory. We can demonstrate this with a simple arithmetic problem, and this brings us to the interactive portion. Anyone got an answer? You can shout it out.
5.
Perfect, it's 5. Good to know everyone knows math in here. So that's a pretty easy one, but I got a tough one for you. What if we add one more?
6.
Amazing, you guys are great. So how did you get that answer? I can tell you probably didn't get 6 by adding up all 6 of those ones again, because why would you? You already knew that the answer to the second problem was just going to be one more than the first problem. So you just used that first problem in order to find the answer to the second, removing those redundant calculations. This is the essence of dynamic programming. We break our problem into subproblems and then accumulate them into our larger answer. Now, applying this to line detection is a bit more difficult. We begin by dividing our image into horizontal slices of pixels. In the first iteration, they're of height 1. And we're going to be looking at an offset, which is a vertical slice of pixels of width 1. So when we look at an offset within our first slice of height 1, it's only going to be 1 pixel. We go through every offset and slice in our image, and that eventually gives us the brightness of every individual pixel in our image. Then we double the height of our slices and cut their numbers in half so that all of our slices are of height 2. We continue looking at those vertical offsets so that our line segments are now a vertical stack of pixels of height 2. But rather than calculate the brightness of those pixels directly, we can instead add together 2 adjacent slices of height 1, stacking them on top of each other to then get that next answer. We're building up line segments, so then we use the slices of height 2 to get slices of height 4 and height 8 and so on. This way, we only have to calculate the brightness of pixels once, and we can simply accumulate those answers in order to get larger line segments that go the full length of the image. And if you want to look at lines at an angle, can simply shift over the slices and then continue to look at that vertical offset so that in the original image, those pixels are at an angle. Now there are two things to note about the algorithm here. Since we're going from a height of 1 to a height that encompasses the whole image by cutting our number of slices in half, our image needs to be of a height which is a power of 2. We do this in pre-processing where we pad our image and make the rest of it, just make the edges black so that it is an even square where the width and edge are even powers of 2. Also with the algorithm, the way that we're shifting our angles over, it only covers an area of 45 degrees, from 90 degrees to 135 degrees. We have to run the algorithm 8 times over the image, rotating and mirroring it so that we cover the full 360 degrees. So let's look at a runtime comparison between our two radon approximations. We're measuring our runtime in what's called Big O time. Big O time tells you the worst case scenario number of steps an algorithm will need to complete a task given an input of size n. Our hue transform runs at Big O of n cubed, while our ADRT runs at Big O of n squared log n, which is smaller. And while it might not seem like a very big difference, it really helps to cut down on our runtime and increase our efficiency. Before we look at the actual results, I first want to show you a little more of the pre-processing we do to prepare the image for the algorithm. The first step is called the image derivative. This is very similar to a calculus derivative. The value of the pixel on the derivative is correlated directly to the change in brightness of its neighbors. So a pixel with a very bright neighbor on the left and very dark neighbor on the right will have a very high value on the derivative. We're highlighting the lines and making sure that the algorithm will work on every single image. Second process is a little simpler. It's called image erosion, and the value of the pixel in the image erosion is simply the brightest of its neighbors. So now we can look at some of the results of the algorithm. On the left will be the original image, and on the right will be the algorithm image. That green line there, it's a little hard to see, is where the algorithm says the line is, and that red dot that I'm pointing to is simply the center of that line. So here's a pretty simple example, just a white line and a black background, nothing to get excited about. Here's something a little more complicated. This is a picture of my laptop, and you can see that the algorithm got 3 of the most prominent lines in the image. Now here's the most significant result I want you to look at, and I want you to look at a specific edge here, specifically this one here. That's a fragmented edge. You can see that it's kind of broken, it's a little faint in places, and on the original image, it's essentially a change between the same color, albeit with a bit of difference in the brightness. And while most line detection software might have a hard time finding that edge, our software finds it no problem, along with all of the other significant edges in the image. Another example of fragmentation here, we have the top of this desk, which is essentially the same color. It's pretty hard to see, but the algorithm still gets it. One final example is this really small tile line, which is even a little hard to see for the human eye, but once again, the algorithm gets it no problem. Just like any algorithm, ours does have its limitations. One of them is heap space. I wrote this program in Java. Java only has so much memory to work with, and sometimes it has a lot of memory to store, so it's storing information for height 1 and 2 and 4 and so on. It's a lot of things to store in memory. Images taken on my phone, which are 4048 by 3036, are too large for the algorithm to run. The ideal size for image is 800 by 800, 1024 by 1024. But since we're navigating indoors, we don't really need super high definition images anyways. You also notice that those green lines that were detecting the edges went to the edge of the image. That's not entirely practical for navigation. We'd like them to be bounded to their particular edges. So this is just something we need to fix in the future. And finally, the algorithm tends to struggle with high noise to signal ratio images. These are images that are noisy or dirty, like this one here. This is the floor of our carpet, or the carpet of our lab. The floor is ripped up, and you can see it's a little noisy, it's a little dirty, and the algorithm tends to give us a bunch of false positives for this. Another thing we need to solve. One final hurdle that we're looking to solve especially is which of the edges do we accept after we finish running the algorithm? Because right now, when the algorithm finishes running, it gives us a table of row theta values associated with every line in the image and their associated brightness value. Our current method for deciding which of these edges are prominent enough to put on the image is called thresholding. We take the brightness of the brightest line on our image, we accept all edges within a certain percentage, say 30 or 40%, and then we weed out the ones that are too close together. They're only a few degrees or pixels apart. And while this works pretty well, it's not ideal, and we can definitely do better. What you're seeing on the screen is called a radon sinogram. Actually, the radon sinogram of the Gaussian, as you saw earlier. This is a direct plot of those rho theta brightness values, where rho increases from left to right and theta increases from top down. And the brightness of a pixel on this graph is the actual brightness of that line. So these bright spots here, which I'll highlight, are those most prominent edges. So it stands to reason that we might be able to use this radon plot in order to find our most prominent edges, and this is exactly the direction the lab wants to go. You can think of those edges as peaks, mountain peaks. We want to accept all of the edges which are at the tips of those peaks. There are a couple of things we need to consider before going through with this. What about the pixels that are just a few pixels away from those peaks? Do we accept those? What if two peaks are too close together? How do we decide what is the minimum height for our peaks? A lot of things we need to contend with, and the algorithm is still in its early stages. So in the future, we would like to solve the bounding issue, solve the noise issue, perhaps by passing a noise filter over the image. We'd like to find a better edge acceptance method. We'd like to more quantitatively determine how effective the algorithm is at solving the fragmentation issue by comparing it with other edge detection software. And we'd like to actually put it on a robot. We'd like to put it on a little Roomba or something, have it navigate around, feed it results of the algorithm, and hope it doesn't bump into anything. So here are the citations for the presentation. I'd like to acknowledge Professor David Chapman, who was my mentor on this research, the Viper Lab, which is his computer vision lab here at UMBC, University of Maryland, Baltimore County, the Leadership Alliance, who I applied in order to come do research here, UMBC College of Engineering and Information Technology, and Professor Martin L. Grady, who published a fast discrete approximation algorithm for the radon transform all the way back in 1998, which is what this algorithm is based on. Thank you for listening. Any questions?
Could you go back to that graph a few slides ago? The one with the, yes. What image was that from?
That was from the sofa, so that's from this one. You can't tell. They all look the same. They all look like that.
All right.
Anything else?
How long did it take for your camera to take a picture of the image?
So the images, you asked how long does it take the camera to take a picture. These are actually uploaded directly to the program. So these are images on my computer that we uploaded to the program, have it run. We haven't actually attached a camera to it yet.
How much more complicated would it be if your object was moving back?
How much more complicated would it be if it was moving? Well, if it's moving, you would have to take a snapshot of it at one particular point. We haven't really thought of like movement that much in terms of like fast movement. For indoor navigation, you would probably move a little bit, take a picture, see where you need to go, move more. You got another question?
Yeah, so do you think this technology will eventually be applied in real time?
Do I think it'll be applied in real time? Absolutely. I think it's very efficient line detection software. It's never been done before, and it fixes a lot of faults with other line detection software. So it's still really early. I mean, I finished writing this like half a month ago. So once we fix the issues, iron out all the kinks and stuff, it'll be all right. Anything else? Over here.
Does the resolution affect the pixel brightness?
Does the resolution of the image affect pixel brightness? No, so the pixel brightness depends on the RGB values. So if you have, even if you have a low resolution image, this can still work. You can't get down to like 10 pixels, but the smallest that it works is probably like a 300 by 300 image. There's another?
So I know that you said the program stores it's a lot of data. So have you thought about using lower resolution?
Yeah, no, you definitely can. You asked maybe the algorithm stores a lot of data. Why don't we use lower resolution? That's definitely a solution in order to help it speed up. Because if you have a robot with a camera, it doesn't really need to take super high definition, 4K pictures. It can do with a, 1024 by 1024 image or even smaller. Anything else? Right here.
So if you're gonna put this on like a Roomba, like just for the example, what do they use now and why is that better?
So Roomba, that was kind of a joke, but Roomba's use, I think, sonar, maybe? I'm not sure. Or they just bump into it and then turn. Current software uses, I believe, segmentation. That's why the fragmentation is a problem, because they segment an edge to see if it's a real edge, and then they'll say, oh, this is not as bright as the previous portion, it's probably on a real edge. So yeah, the robots that we would probably put this on would probably be just those little, four-wheel robots that wheel around. I don't know how Roombas work. Anything else?
process of image erosion. So, do you do that manually before you give the photo to the software?
It's not done manually, it's a separate program. So within our pre-processing stage, the program runs all in one loop, so you just press one button and it gives you your image. So that's the first thing we do before we pass it in. It's in the constructor, if anyone knows Java. And that just does all the pre-processing and then passes the resultant image, which is the derivative and then the erosion applied onto that derivative. Anything else? All good? Okay. So thank you very much for listening. Our final presenter is Afia Ose Intansa. You guys are gonna like this one.